Let's execute this program. In C, execution always starts from the main function. The CPU runs code line by line. X is assigned 10, Y is assigned 20. Now we hit a function call. X equal to add of X and Y. Execution jumps into add. The function runs and eventually hits the return statement. Function is done. But now, where does it return? There are two calls to add in this program. From inside add, both calls look exactly the same. So how does the CPU know this time return to line 8 and not line 9? And there is another problem. When add was executing, main was paused right here. At that exact moment, main already had x equal to 10 and y equal to 20. That state has to come back the moment add returns. Does the CPU re-execute main from the top to recover those values? No, that would break everything. X and Y would reset. So, where was the main state stored? How does it recover its entire scope the instant it returns? Keep these questions in mind. We are going to answer all of them. But first, some foundation. Hey, I am Trijant. In the last lecture, we zoomed inside process memory. We saw that every program runs inside its own virtual address space, divided into four major regions. At the bottom sits the code segment, where the machine instructions of your program live. Above that is the data segment, where global and static variables live. Then comes the heap, the memory used for dynamic allocation through functions like malloc or keywords like new. And finally, at the top, the stack, the region responsible for managing function calls and local variables. Now, those questions we just saw. Where does the CPU return after a function call? Where does main state survive while add was running? The answer to all of them lives right here, inside the stack. But here is the problem. If I take you inside the stack memory right now, it will not make sense. Not because it is complicated, but because there is one concept you need to understand first. The stack, not the memory region, the data structure. Stack memory is named after it. It behaves exactly like it. And if you do not understand the concept, the memory will just look like numbers moving around with no logic behind them. So that is where we start. A stack is one of the simplest yet most fundamental data structure in computer science. And it has one rule, just one. The last element that enters is the first element that leaves. Let me show you with something you already know. Think about a cafeteria tray counter. Empty for now. The worker places the first tray on the counter. A second tray goes directly on the top of the first, and a third tray on the top of that. Three trays, but only one is reachable right now. The top one. The tray below are completely blocked. You cannot reach them directly. What if you need the bottom tray? You have no choice. Remove everything above it first. So we remove tray 3 first, then tray 2. Now tray 1 is reachable. The one placed first is the last one out. Tray 3 went in last. It came out first. Tray 1 went in first. It came out last. Last in, first out. This is the one rule that defines a stack. Last in, first out. Now let us see the same rule with actual data. The way a computer sees it. We push the number 10, push 20, push 30, three values 10, 20, 30. Only 30 is reachable. It is the top. Which one can we remove? Only 30. Now 20 is the top. Pop 20. 10 remains. Same rule as the track. Last in, first out. Let us give this operation their proper names. Adding to the top is called push. Removing from the top is called pop. And reading from the top without removing it is called pick. Push, pop, peak. That is everything a stack gives you. No random access, only the top. Now you might think, this seems like a very limited structure. Why design something this restricted? Because the restriction is the point. When you restrict how data can be accessed, you create predictability. And predictability is exactly what a CPU needs when managing function calls. Now let us connect these two function calls. But this time, imagine a deeper example. Say main needs to compute a multiplication, so it calls multiply. Now multiply internally uses repeated additions to do its work, so it calls add. Three functions, all running, but only one is actually executing right now. Add. Main is waiting for multiply's answer. Multiply is waiting for add's answer. Only add is doing the work. Now, in what order do they finish? Add was called last, so add must finish first. The moment add returns, multiply can resume. It was waiting for the result, and only after multiply finishes, main can continue. The function called last is always the first to finish. The function called first is always the last to finish. That is last in, first out, happening naturally inside every function calls in every program ever written. This is not a coincidence. That is not a design choice someone made arbitrarily. It is the fundamental nature of how functions nest. And it is exactly why the stack, with its last in first out rule, was chosen to manage function calls in every major CPU architectures in the world. Now we understand what a stack is. We understand last in first out. We understand push and pop. But remember those two questions from the beginning? Add was called twice. How did the CPU know exactly which line to return to each time? And when add was running, main was paused right here. X equal to 10 and y equal to 20. Where was that entire state kept? How did main recover it the instant add returned? The answer to both questions is the same thing, the stack frame. Every time a function is called, the CPU pushes a stack frame onto the stack. That frame holds everything that function needs: where to return, all its local variables, its entire execution context. When the function returns, that frame is popped, completely gone in one operation. That is how the CPU knows exactly where to return. That is how main's state survive. That is last in, first out, working silently behind every single function call your program makes. But what exactly is inside that frame? Just a return address or something more? How does the CPU build it? When exactly does it get pushed? When does it get popped? In the next lecture, we go inside a stack frame. We will see exactly what it contains, how the CPU constructs it, and how the entire function call mechanism works at the hardware level. By the end of that lecture, you will never look at the function call the same way again.